apparently there are some problems with the sound. Please interrupt me when the problems become so severe that you cannot follow what I'm saying. And please interrupt me whenever you don't understand what I'm saying. In general, I start the course by losing in quotation marks, the first lecture by making a tour of the participants and trying to understand the background of each of them so that I can adapt the course to the audience. But this year I will do the opposite. I will start with a lecture, which I'm trying to make it quite simple. I already made it simple, the course, during the past year when I gave it to Avnipina. And but it still could be that some of the things are not, you cannot follow them. So please interrupt me and ask me. It is very important for me that I don't speak to the walls and I speak to you. So so I will start now the lecture. And again, I insist that you interrupt me. Sometimes even when I give lectures to professional audience, I say that I cannot speak if I'm not interrupted. So please take this into account. So the course, it's about very dramatic, rare events. You know, like economic crisis or like an epidemics, which are very rare. So if you think in terms of probabilities, you would say it's negligible if it happens one in 10,000 possibilities. But if the event is large enough, then it can be a very decisive. For instance, the zoologists are telling us that there was a few hundred million years ago, a big meteorite which hit the Earth's surface, and because of this, raised a lot of chaff, and then there was not enough light and heat, and therefore the dinosaurs disappeared, and the mammifers took off, and this is how we are here instead of the entire planet being inhabited by dinosaurs. So this is the kind of event we are speaking about. Of course, I personally, I'm not so much interested in dinosaurs, but when it comes to economic crisis or epidemics, or even viral memes, and of course revolutions and things like that, then it's important to try to understand. There are quite a lot of discussion about this, especially after 2008. One of the traders, which was lucky enough to sell before the crash, invented the concept of black swan. Of course, there was the story of the black swan already from the ballet and things like that. But essentially, he said if you studied all these swans in Europe and you see that all of them are white, then the probability that you find a black swan, you would attach to this 0. But if you go to Australia, there are black swans there, and out of a sudden something which, so to speak, mathematically wasn't expected would happen. So this is why I'm starting with a standard probability function. Is anybody which didn't hear yet about the normal distribution, which is also called the Gaussian distribution, which is also called the Bell distribution? It is important for me if somebody didn't hear about it, because then I will, when I explain it, I will go slower than otherwise.
I didn't hear about it, so I would be happy if you can explain.
You didn't hear about that. Okay.
Yes.
Okay. So, the Gaussian distribution, which now I'm very happy that I dedicate a lot of today's lecture to introduce this distribution. It's about this. Let me start with I will essentially what first of all, I should emphasize the distributions which we are going to discuss are not the normal distribution, but the normal distribution is so to speak what would be expected in a world which didn't have surprises, which didn't have revolutions. So I'm starting with this. So, so I will explain to you what is your name, the student which just answered me.
Raham.
Yeah. So from now on, during this explanation, from time to time, I will check with you if you agree with what I'm saying, if you follow what I'm saying. So, so the best way to explain how this object, the normal distribution appears, is to speak about throwing dice. Again, I personally, I'm not very much interested in games which depend on dice, because I think of myself of being better when it comes to thinking. So going to a purely random and depending only on chance, I think it's not a good strategy for me. But let's try. Now, if we throw the dice, and if the dice is not tampered with, if nobody tried to tamper with it, to make some number appear more than the others, then the six different outcomes have equal probabilities. So these blue bars are, so to speak, a measure, a visual measure of what is the probability of each of the sides to appear. And of course, they have equal probabilities. Is it okay until now? Is it understood what I'm speaking about?
Yes, I think I understand what is a normal distribution.
No, until now, no, this is not the normal distribution.
No,
no. It is what?
Oh, no, I understood what I meant that I understood what you said. What you said now.
Okay, in this case, I'm going to be a little bit too slow for you, because I'm still going to explain. Maybe there are other students which didn't dare to speak as you did, and you did very well. So what happens if you throw two dice instead of one? If it is one, it is this is a constant distribution. Constant because if I go from 1 to 2 and to 3, I get the same thing. So, but if I throw two dice, then the situation is like this. If I cannot get 0 or 1 because each of the dice start with 1. So the lowest number which I can get is 1 and 1. 1 for the first dice and 1 for the second dice. So the sum of them is 2. Now, however, if I ask in how many ways I can get 3, then it's more than 1, because there could be 1 and 2. the first dice to be 1 and the second to be 2, but it could be that the first one is 2 and the second is 1. So there are two possibilities. So the probability is twice as much. The probability to get 4 is 3 times as much, because it could be 3 and 1 or 1 and 3 and 2 and 2. Is it clear until now?
Yes.
Okay, so I get this distribution. This is, I would call a triangular distribution, because as you see, it looks like a triangle. And I'm not going to calculate the other possibilities, because you see that it just adds one more possibility for each number until 7, and then it decreases, because, for instance, to get 12, there is only one possibility, that I get a 6 and a 6. And this we all of us remember, because if we want a big number and we want a 6, 6, we know that it's not very probable. Now, what happens if I have 3 dices? Then one can compute in the same way how many times I get 3 and how many times I get 4 and how many times I get 18, because 18 is the maximum. It's when all 3 of them are 6. And as I go with more and more dices, I get a distribution which is looking less like a straight line like here, and less like a triangle here, and it looks like a bell. And this is sometimes people call it a bell distribution, and people also call people which think that they know mathematics, they call it Gauss distribution, even though, as it happens very often in science, the credit is not deserved by Gauss. Gauss was so great that he invented so many things that they attributed this discovery to him too. But it was actually another scientist, much less famous, called Moivre, and he was the first which discovered this bell distribution. In fact, he discovered it in the context of writing an entire book about luck games. But he actually didn't speak about dice. He spoke about coins, throwing coins. And I'm going to explain now the coins, but first I will check with you if until now you kind of understood.
Yes.
Good. So how Moivre did that? You don't have to remember the name of Moivre, because now, since I'm a professor, you believe me that it's Moivre and not Gauss which invented it. But if you will say it to your friends, then they will say, no, you don't know, it's Gauss. And people call it Gaussian distribution. In any case, Moivre did the following experiment, or actually what is called thought experiment. Thought experiment is a concept which is very important in science. Actually, when Einstein discovered the general relativity, and he was thinking in terms of experiments, which actually he never did. He just imagined in his head what happens when you do this experiment, and reached the conclusions which he reached. So Moivre, I suppose, even though he was a player, I think that it was his profession to play this kind of games. But when he wrote the book, this is an imaginary experiment. So you throw once a coin, and of course there is half of the times that you throw it will be heads, and half will be tails, and so there is probability half to be heads and half to be tails. And then what happens if you throw again? Then again, if you had a head, this doesn't influence the outcome. There will be still a probability half for the next time that you throw the coin to come a head or a tail. And the same thing happens if you had tail the first time. You could have a head or tail, and you can throw the third time. And now you can ask, what is the probability to have 3 times head, or 2 times head and 1 time tail, and or 3 times tail, and you could do this for a longer um, uh, chain of throwing the coins. And here I'm making this. You see, you start and you have the possibility to have a head or a tail, and then you have equal probabilities if you had a head to have a head or a tail. So when you take into account all the possibilities, you are left with these possibilities, each of them with equal probability, because each time that you throw, it doesn't matter what you got before. You could get with equal probability a head or a tail. So now you can count how many times you got 3 times head, 4 times head if you had 4 throwings. So if you look here, there is only one H, and this is only one. How many times, how many possibilities are for getting 3 heads and 1 tail? There is one here, and there is a second one here, where the first one is when the tail is the last throw. This is when the tail was the third time. This is when the tail was the second time, and this is when the tail was the fourth time. Do you see what I'm doing?
Yes, I see what you're doing.
So I'm counting what the different possibilities to have 4 heads or 3 heads and the tail, and the next possibility is to have 2 heads and 2 tails, and this is 6 possibilities, and to have 1 head and 3 tails, and to have 0 heads and 1 tail. So there is this probability which looks something between a flat one and the triangular one. It's so I can do the same thing with 6 times, and I'm not going to count anymore. But you see here, and I colored in different ways the different outcomes in terms of the sum, and so you see that there is if I have 3 throws. Then there is not 3, 5 throws. Then there is only one way in which I get 5 by getting each of them head. But there is 5 ways of getting 4 heads and 1 tail. So these are the 3 green, the 5 green outcomes. And there are 10 ways of getting 2 heads and 3 tails, and also 10 ways of getting 3 heads and 2 tails. So the distribution of how many heads and tails I get, it's this distribution: 1 for 5 heads, 5 for 4 heads, 10 for 3 heads. Also 10 for 2 heads, 5 for 1 head, and 1 for 0 heads. And this is what happens if you take more throws. For instance, this is if you have 16 throws, then there will be a higher probability to get 8 and 8. That half are heads, and there will be lower probabilities to get 0 heads or to get all the 16 heads. So this looks like a bell. This is not exactly the Bell distribution, the Gaussian distribution, the normal distribution, but it's very close to it. The one which is rigorously speaking the Bell distribution is if I have an infinity of throwing the coins, and then it's exactly the Bell. But from now on in the course, whenever we see this kind of thing, we'll say that it's the Gaussian distribution, which, as I said, is not correct because it's Moivre. But it's definitely a Bell distribution, and we will question whether it's normal, in the sense that until recently, people thought that most of the distributions in the world are normal distributions like this. And it became clearer and clearer lately that this is not really the case. I think that the first time that somebody paid attention that the distribution is not really Gaussian, it's not really normal, was then about 100 years ago, some British officers started discovered Egyptian hierographs, which were the accounting of the height of the Nilus in different years. It was terribly important for them because it was essentially if they had what to eat or they didn't have what to eat. It depended on what was the height of the Nilus River in that particular year. So they have statistics for the thousands of years from what I remember. Incidentally, nowadays there is great tension between Ethiopia and Egypt because Ethiopia constructed a dam for the waters of the Blue Nilus, which is in danger of making less water in the Nilus. So it's terribly important for people which live there. So this British officer made a statistics of what was the fluctuations of the waters of Nilus over many hundreds and thousands of years, and he discovered that it wasn't Gaussian. What does it mean it was Gaussian? It means that there were some years in which a lot of people died because there were floods, and there were a lot other years in which a lot of people died by famine because there was not enough water for the food to grow. So this is actually in the physics department at the Hebrew University. There was a machine like this in which you see what happens. But before that, I ask again. Until here, everything is it's understood, or do you have questions?
No, everything is understood.
Okay, so here is a machine which is essentially the machine in the physics department is not so beautiful, and the balls are not colored there. But this is the beauty of mathematics, that or whatever I'm teaching now, which is not really mathematics. It's as always in physics, between the real world and the imaginary world. I'm speaking about numbers which don't appear in the, you don't see in the sky a 4 or a 5 appearing. So it's in our head, but it represents things which happens in nature. So here is a machine which is producing a Gaussian distribution, because it's essentially a little bit is the same mathematics like throwing the coins. You see, there are balls which come from above, and here there is a little thing which forces the ball to go either right or left, not to stay there. with equal probability. And then once he's there, he also can go right or left with equal probability. So it's exactly like the things, the drawings which I made about throwing the coin, and there is and then I had to count. Uh, and then I had to ask you if you agree with my counting or not. But the machine doesn't ask anybody. It just stores the balls, and as you see, it gets very close to Bell distribution. So it enforces the impression that this is a normal thing in which things happen in nature. And as you remember, my entire course is going to be after the first lecture that things in nature don't go that way. And it produces a hell lot of problems. In particular, the wealth of people is not distributed by a Gaussian, by a Bell distribution. There is usually we were giving the example of Bill Gates, but now it's not Gates anymore. It's what's his name? The one from Amazon. What's his name? Yes. And he has so much money, and we have much less. So it's definitely not a Gaussian distribution. And we'll see what it is and how it happens. And even though we are envying him, you'll see that it's probably not his fault that he's so rich. Okay. And here, so essentially in this machine which I was describing, and this one looks a little bit more like the one in the physics department. It has all the balls of the same color. Essentially, the number of balls in one of these places is proportional with how many ways you can get to here. So, for example, in 6 you can go in this way, but you also could go, like this, so there are many ways, and this is why so many balls are ending here, and there is only one way in which they can end here, and this is why there are only few of them. So you might think that from my examples until now, that this kind of distribution appears in this kind of semi-mathematical situations in which one can go one step right and one step left, or one more throwing for head and one for the tail. But actually, the situation is not like this, and there is a lot of mathematics to prove that if you just throw darts into a kind of place like this, then you make errors. Not always smack in the middle. It depends also on, of course, this is dart throwing, which let's say I would do because I'm not good at throwing, and this is closer to what the champion would do. You see, most of the throws are very close to the middle. So in my case, the distribution, the probability would be like this. You see, now I'm making a step which I'm checking with you now if you agree. Until now, the graphs which I was making were made by this kind of columns, and now I'm approximating the columns with a continuous line. But it's the same shape basically, except that there could be shape for the ones which are good at throwing darts. This is the distance from the middle, and there is another curve, but it's still a bell curve, which is for people which are less good at that. Is it okay?
Yes, good.
Okay. now we start to understand that it's not for nothing that people call it normal, because it's this probability distribution appears in many places. In particular, for instance, suppose that I want to measure the length of a screw. Definitely, this happens probably every day, every minute in places where they produce screws, and they have to have a given length. And then there is somebody who is checking the quality of the production of that screws. Incidentally, since I was taught by people which are teaching pedagogy to the professors, which is very necessary, because you maybe don't know, but the selection of professors at universities is not according to how good they are in terms of pedagogy, but in terms of how they are quoted, their articles are quoted by their peers in professional journals. So typically we are very bad at pedagogy, but now there is a department at the university which they are teaching us how to be more pedagogical, and they say that every 20 minutes we have to make some jokes. So one of the jokes is that a company from the United States are ordering from Japan some 1 million screws like this, and they ask that only 100 can be defectuous to not be exactly as ordered. So I don't know if it is 1 million. It should be 100. It's I don't know, probably 1 over 10,000. So 0.01% they accept that there will be defectus. So the Japanese send them the order, and there are 1 million minus 100 screws, which are exact, and they put in a little bag 100 screws, which are not exactly the right dimensions, as the customer asked, which of course it's a joke, because the point of the Americans is that they didn't want to have more among the delivered things. They didn't insist of having the wrong ones. Anyway, returning to this, if somebody makes the measurement, or if many people make the measurements, of course there will be they will get not absolutely exactly the right length. There is an error in measurement. Maybe they don't put the screw exactly horizontal. Maybe they press too much the key, and then they get a smaller thing, or they are very they don't touch it very strongly, and then they get lengthy. And if you measure all these measurements, you'll see that they have a bell shape, and they have a mean, which normally you would associate with, so to speak, the real length of the screw. And they have this kind of errors, and you can define what is the standard error by looking at different heights in this distribution. But so I'm not insisting that you understand what I said in the last few seconds, because in fact I didn't say very detailed. But the point is that if you make a set of measurements, you would get typically this normal distribution. So this is another way in which the normal distribution appears in nature. And the same thing can happen when you measure times. For instance, you probably remember that Galileo Galilei measured the gravitational acceleration by measuring the time by which a stone would fall from a given height. And again, in order to measure it, you have to be very precise in starting the chronometer and in stopping it. And you make errors on it. And if you look at the distribution of times, which you get, again, there will be not always exactly the same time, but there will be a medium time which you would think that this is the real time, and there will be some variation of it, which is parameterized by the width, so to speak, of this bell. It's okay until now? Are there questions?
The highest columns are the most correct ones?
It is higher because there are many measurements which had exactly that value. So in terms of probabilistic, if you have 100 people measuring something and 99 of them say that it's 5 meters and one of them says that it's 4 meters and a half, then you would believe that it's 5 meters. And because of this, yes, the highest column is not defined as the most correct one, but it's just the number of people which gave that result. But it's very probable that it's probably the right result. However, as you see in this particular case, the highest region. Can you see the little cross which and the arrow, the little arrow on the screen? The one which I'm moving just.
Yes, we see it.
Okay, so we see this is how many measurements gave this particular. Let's say that this is 60. 1, 2, 3, 4, 5. So this is 62, something between 62 and 64. So most of the people, most of the measurements were here. However, if you look at the other measurement and you fit it by, you try to put a bell shape which fits best this thing, then you actually get 0.6. So the convention is that in spite of the fact that most of the people among the other possibilities gave the number between 62 and 64, you think that the length is 60 because otherwise you'd fit less the Gaussian. But this is a kind of is an entire profession. I mean, looking at numbers and deciding what you believe is the correct thing, it's not what I'm going to teach now. And actually, I don't know myself much about it. But okay, so this is the answer. That in principle, yes, when many measurements give some result, you think that that result is much closer to reality than values which were obtained much less times. And so until now we we saw that the normal distribution appears when you throw coins or when you throw dice, and when you throw darts, and now when you make measurement either of length or of timings. But now we see that it appears also in things in which we are not really involved. We are not throwing anything, we are not measuring anything. We are just looking at what are the weight of babies when they are born. And again, as you see, there are here a little bit of deviation from the Gaussian distribution, because there are premature babies which can be born, and then they obviously don't have at birth the weight which they would have if they were born at 9 months, if they are born at 6 months. So there is here some number of babies which are higher than the black line, which is the Bell distribution. Do you understand what I just said? I mean, if you believe in that the Gaussian distribution is the correct one, then these things shouldn't happen. And indeed, when they happen, they are called premature. They are kept in special conditions. So in a sense, there is a lot of information, even when something is not a normal distribution. Are there questions? Okay. So this is as opposed to babies at birth, you can think about the height of people, and at the time when they measured it in 1900, they couldn't oblige people to be measured. But of course, if somebody was a criminal, then he was obliged to be measured by the police. And you see that it's quite a good fit for the Bell distribution, the height of people. And here is also for women. As you see, there are deviations, because in this particular experiment, they didn't have many people. But if you take billions of people, then you would be much closer to this exact Bell distribution. And here is a measurement which actually I don't like it very much, because they measured the how many sales they had for different sizes, but they did it only for women, and with implication that they buy more shoes, which might be true, but it's not politically correct to say so. But now you can start to see that it's important to measure this kind of things, because if you measure this, then you know how many shoes to produce of each size. If you produce too many shoes of too small size or too large size, you will not be able to sell them. And on the other hand, if you don't produce enough of the medium size, then you'll miss the opportunity to sell more. So, so this kind of statistics are pretty important. They are also this is important for me, because I have blood pressure, big blood pressure, and as you see, more or less the distribution is Gaussian, and there are some exceptions here, which are people which have too much blood pressure, which is not good. So they have either to take pills, and if they don't take pills, they have to eat less. And if they don't get pills and they don't eat less, then they will end up needing this kind of ECMO machines, which are for helping people which have heart attacks or other things. And if this doesn't help, they will die. So measuring how many people have this, it's important. By the way, I see that this graph, this columns, the blue columns, as you see, they are very noisy. They are not exactly fitting the red line. Maybe they didn't make enough statistics, but and you might, because I didn't show you any other graphs than the bell one, you might think that this blue columns could be fitted better by some other graphs. And but when you see other distributions, the ones which are interesting as I told you, these Gaussian are the ones which I'm showing you in order to show to you how could be the world, but it's not. When you see the other ones, you'll see that they are very different from the Gaussian, from the Bell distribution, and you'll see that the blue thing is really well approximated by the red line. So this is a SAT scores, Scholastic Aptitude Test. And again, it's important to know, because it's important to know how many geniuses you expect. And it's also important because below a certain level, you don't want, for instance, to take them in the United States Army. There is a limit below a certain number here. They are not allowed to take them in the army. And this is the IQ distribution, again, very close to the bell. So now I think that I bored you enough with the bell distributions in order to explain to you that in spite of the fact that it appears in so many different contexts, in fact, when it comes to things which are important socially, especially when we are speaking about collective effects, about a lot of people, then what happens is very different from the Bell distribution, because you see in the Bell distribution the range is very close. There is the average, the mean, and there is a certain range above and below, and outside that range there are not really events which happen with that value. Like you'll not see a child which is born 10 kilos, or a person which is larger than 2 meters and a half, or a person which is smaller than half a meter. So all in all, we are speaking about quantities which are limited in a very limited range, and this doesn't happen at all in many other situations which are very important for us. When it comes to celebrities, most of us are known by 500 people, but there are people which are known by millions of people or billions of people. So definitely we don't expect that to be a Bell distribution, and in fact we will see which kind of distribution it is. And in the course we also explain how that distribution takes place. And the same thing is about wealth, which is a very touchy subject, and during the history there were revolutions around these things, that there are people which were too rich and people which were too poor, and then there were enough people which were too poor. Then they would say, you know what about killing the rich guy and getting his money? And even now in the United States, there are in the Congress, there are people which are saying, let's take the money from the rich and pay, I don't know, the college fees for the poor. Which, by the way, it's not. I'm not relating to whether it's fair or not, but it wouldn't be enough, even if you take the billions of Gates or of the other guy from Amazon. It would not be enough to pay all the college fees for everybody in the United States. So it's more complicated, but we'll see that. Incidentally, I personally, I'm very tolerant in terms of political views. Even though I have some antipathy for you know, communist or fascist the things which are more related with the fact that those regimes led to death of people. But I'm very tolerant please feel free during the course to express your views about that, because it will give a little bit color to this, because the way I'm going to speak about you know, wealth and contagion and things like that, it's a little is intentionally dispassionate. I'm trying to speak in terms of what the numbers say, but these are it's legitimate for some of you to feel passionate about it, and I encourage you to express it and to contradict me if you think that I'm speaking things wrong. So there are two ways, two reasons to interrupt me. One is when you don't understand, and one way is when you don't agree, which is there is a third thing, that maybe about some things you know more than me, and then you can tell me that. Then there are also non-Gaussian distribution when it comes to influencing people. There are people which are influencing millions, and there are people which don't influence anybody. And of course popularity, and for a scientist, for somebody like me, for instance, what is important is how many publications and how many citations you have, and that also is not, unfortunately, is not Gaussian. So I don't have so many as other people have. There are people which have 20,000 quotations, and I have only 10,000. But of course, there are people who have 100. So so it's not Gaussian. Somebody when HIV started to be important, which fortunately for you it wasn't during your generation, it became also fashionable to count the number of sex partners, because it was related with transmitting HIV disease. And they found also power. There are some people which have a very low number of sex partners, and there are people which have a lot of partners. And in fact, there was an explanation of the start of the HIV disease about some waiter in one of the planes which were going from Congo to Canada or something, and which he had a lot of sex partners, and he was supposed to be the one which brought HIV from Africa, from the woods of Africa to the civilized world. But from what I remember, lately they said that this research wasn't reliable, and that they blamed him for nothing. And he was dead anyway by that time, of course, of AIDS. Anyway, the thing I mentioned that this had to do with contagion, and nowadays we are very much interested in contagion, and we'll see that in contagion too, the standard statistics which leads to the Bell normal distribution is not the correct one, and there are other things. Of course, speaking about statistics in contagion, it's a little bit discredited nowadays because there were so many people, and among them many physicists, which started to speak about it, and in the end they weren't right, many of them. So I wouldn't blame somebody which would say, let the physicists do physics and not bother us about the statistics of corona. Okay, so now we finally, what is the time now? It's almost 1:30. I spent 1 hour for describing the Bell distribution, and now I'm going to start describing what really happens in nature in many occasions, in most of the occasions which are important for us. So this is the first graph in which you see the difference. This is the normal distribution, and this is what is called the log normal distribution. I will explain very how do you call it? Not nicely. Very carefully, what is this log normal distribution, so in such a way that that everybody hopefully will understand. And if you don't understand, again, interrupt me, because the scope is not to hear myself speaking, but to try to teach most of you this. So in the meantime, I'm not at the point of describing why is this maroon line, red maroon line, is called log normal distribution. All I'm telling you is that it is that way for many things, and it's responsible for catastrophes. And this is what I would like to explain to you. You see, if for instance, the number of dead people from corona would be a Gaussian distribution, then you would see that it will end with a number between 0 and 2, and maybe between 0 and 20, but it would be a limited amount. While if the graph it's like this, you see that even for very large values, there is a probability that it will happen. And indeed, I will show you the data in a few minutes, in fact, the data in which there are very large values which actually happen. That, for instance, if you make the statistics for the states of the United States, you'll see that there are some states which are definitely outside that range, and they are like New York was at the time, and therefore the reality is very different. And during the course, we'll explain how this happens. in any case, this difference between the belt distribution and this other distribution, and there are a few of them, but not too many, so you shouldn't get scared by it. In any case, the ones which allow for very large values means that, for instance, when there is a fire, there could be a fire of one house or two houses, but there could be fires like you see on the TV, like there was recently in Australia, and there is almost every couple of years in California, in which we are speaking here about fires which are of the size of an entire country. So definitely the difference between Gaussian and that reality is very big, and we want to understand why, not only how, but why, and whether maybe one could, if not prevent it, at least prepare for it. Like in the case I explained to you before about the black swan. There are black swans, and people didn't know about that. But if they knew about that, then they could they wouldn't say that there is not such a thing. And this is what happened with the crisis in 2008. The economist thought that the distribution of fluctuations in the prices of housing is, let's say, Gaussian. And in reality, it was like this. So all of a sudden, in place of having only an increase or a decrease, in fact, in that case, of 40%, it was in some cases in New York. I have seen houses in very good places which were not even inhabited anymore. And about migrations is the same thing. There is one thing to have a few thousand, tens of thousands of people, let's say, traveling between the United States to Israel, or from Israel to United States, or from France to Israel. And there is another thing to have tens of millions going from various countries into Europe, and really leading to a lot of suffering, both of the Europeans, but not that much suffering, but suffering of the very people which were migrating. There were these pictures of people died on the shores, and children and things like that. So this departures from the Gaussian distribution are the very things which make the catastrophes in this world in terms of migrations, revolutions, economic crisis, financial crisis, epidemics, floods. How is it called? Hurricanes, earthquakes, fires, famines, ecological extinctions, as I explained to you, that we are, in a sense, the result of an ecological extinction of the dinosaurs. Here is almost the same graph, except that I took a much longer view of the x-axis, in order to show that even though the probability of very, very large values, let's say very large value of the energy of a hurricane is not very probable, it's still much more probable than you would think if you would believe in the Gaussian distribution, because in the Gaussian distribution, after this point here, practically it is zero. Here it is very small, but even if it happens one every 20 years, it's too much, because it's like there was this tsunami in Indonesia, in which hundreds of thousands of people have died. So even if it happens only every 20 years, it's very important. It's not something to say, okay, it's a very small value compared with how much it's the probability of nothing happens. So so it's negligible. It's not negligible. And of course, this happened in the news when somebody discusses the number of deaths from corona, how much is acceptable and how much not. Of course, if you think in terms of moral speaking, one person is too much. We don't want anybody to die, not even our enemies. But when you speak about an entire country, then the question is indeed, what do you prefer? Having one person, which is statistic, and it's not that you choose a person like they did in the antiquity. They if they had an epidemic, then they would pick up somebody, usually somebody very valuable, some person which was very beautiful or very intelligent. And they would sacrifice that person in order to convince the gods to relinquish the epidemics. But of course, nowadays we are very far from that, and we are speaking about the probability. One in the 10 million people around will die of corona if we don't stop all the activity in the country. Then it's a question. And of course, this question we are encountering with the cars. Whenever I get in my car, I know that there is a certain probability that I will get killed, or worse, that I will kill somebody else if I'm not careful. So, so these probabilities are in a sense governing our lives. So, in addition to this shape, which I called log normal, there is another shape. Meantime, we are speaking in terms of shapes. And in fact, I will never give you the formulas for that. Another shape is the Pareto shape. Who didn't hear about Pareto?
I didn't hear about it.
Okay. Say more. I know that one or two didn't know, but I want to know if maybe nobody heard, and then I would be even more detailed in describing Pareto. Not now, but when I reach to it. So it's Nama. Who else?
I never heard about the Pareto law.
Vladimir. Okay, two. There are
Me neither.
Three. 4.
I've heard about it, but not as the Pareto law. I heard about it as the 80-20 distribution, and I don't know what it means exactly.
Okay, good. Okay, so I got enough information.
5.
This is what I wanted to know. That there are some people which never heard about Pareto, and some which heard about the 80-20 curve. And by the way, it happened to me about 20 years ago that I kind of reached this kind of curve in one of my research, and then I told a colleague about this, and he was Italian. So he said, oh yes, there was somebody which discovered it before. And I was jealous. I said, okay, but maybe I should have published it much faster because somebody else did it. So I asked who, and he said Pareto. And when I said, when did he publish it? And he said, well, about 100 years ago. So this was pretty humiliating, but it was more humiliating the next day because the father of one of the friends of my daughter came to take her back home. she was sleeping at that, and he was functionary, kind of in the Ministry of Health. So he asked me, so what are you doing? And I'm saying, well, to my shame, I'm looking for something which I'm making my own research, but I'm looking in the Encyclopedia Britannica about some guy. And I told myself, well, why should I tell him the name of the guy? He certainly didn't hear about that. But I automatically said, somebody called Pareto. And he said, oh, yes, I know about Pareto, the 80-20 law. So this was a final humiliation. I mean, I was thinking I'm doing research and some functionary in the Ministry of Health knows more about it than myself. In any case, so it's not a shame to not know about Pareto, but after this course, you'll know a lot about Pareto. Essentially, and here I really need, I'm sorry, what was the first student which I asked her to interrupt me? What was your name?
Raham.
Say it again.
Raham.
Ra?
Raham.
Ra. This time I need your help. You should tell me if you understand what I'm saying now. The
Yes,
Pareto,
no problem.
the Pareto law is saying that the probability to happen something, let's say, for somebody to have, let's say, wealth of a certain value is proportional to 1 divided by that wealth. So if somebody has, let's say, if there is 1 million people which have, let's say, 1,000 shekels, then there will be 100,000 which have 10 times more, which have 1,000 shekels, and so on. So each time you grow the power, the number of people which have it, it's by that number less. So if you ask of a wealth which is 10 times more than a certain wealth, then the number of people which have that wealth will be 10 times less than the people which have the first wealth. I'm aware that I didn't explain it very well, so this is why I'm asking you, Ram, if you still understood with this level of explanation, or I should be more explicit.
I think you should be more explicit, and if you must use mathematics, if you don't have to use mathematics to explain it, it will be easier to me to understand. Or just do it very slow so I can.
Okay, so it's like this. Suppose that there are we have 10 friends which have one shekel, and then if the distribution of wealth among your friends is a power law, then the number of friends of yours which have 10 shekels would be 100 divided by 10, because the wealth is 10 times more, then there are 10 people, 10 times less people. So if there are 100 people with 1 shekel, there will be 10 people with 10 shekel, and there will be 1 person with 100 shekel.
Okay. I understand it when it's. Yes.
I oversimplified it, but it's enough to understand this shape. This shape,
yes.
This shape is saying exactly this, and as you see, and the way I explained now, it's not mathematically correct, but it's close enough for you to understand that you see the shape which this probability distribution has is very, very, very different from the normal distribution. And in particular,
Yes.
it implies a lot of inequality because there are a lot of people which have almost nothing. And there are going to be some people, not many, but not zero. You see, here with the red curve, with the normal distribution, there will be basically nobody which has more than this. But with a yellow thing, there will be people even I don't have on the screen 1 meter to the right, but even 10 meters to the right, there will be still somebody which has that wealth. So there will be Jake or the other one, which is there. So this is more or less Pareto law. He discovered it, as I said, in 1896 or something. He made the statistics of the wealth of people in Italy and in Germany and in France, and he found that all of them, they had the same shape. So you see, if the same thing happens in so many things, there is something to research, because it's not that it just happens. There is probably some mechanism which leads to this. And this course, in spite of the fact that I'm not going to use mathematics at all, will explain to you how this happens. I mean, when I say I'm not going to use mathematics, I will use the mathematics which I just used a few seconds ago when I said 100 and 10 and 1 and so on. I I take the liberty of not considering this mathematics.
Yes,
When we go to buy things in the supermarket, we use numbers, but it's not mathematics, it's numbers.
yes, it's right. Thank you very much.
Okay, so the objective of this course is to study how this happened, what are the causes for this happening, and what are the consequences. And this is why I invited the people which have, you know, socialistic opinions to interrupt me, because even though I will try to be very neutral when it comes to this kind of positions. I don't call them political because they are more social, so to speak. But when I will get to this, if I look for causes, even if I look for causes in terms of mechanisms which are formulated in an impartial way, there still can touch some sensitivities, and in a sense, I'm happy with that. I'm willing to listen to it. So in the same way in which I explained to you how the Gaussian distribution, the Bell distribution appears in different places, I'm going to continue in this lecture to explain to you in which condition, in which context the power law distribution appears, the Pareto distribution appears, without explaining yet. The explanation will be, as I said, this is why I need a course and not an evening lecture. It will take some effort, but again, I promise that there will be no more mathematics than, let's say, in the primary school. And this is because I actually worked on it in the previous years when I gave this course. When I started to give this course, let's say about 10 years ago, indeed it was an awful course. It was full of mathematics, and every year I divided by 2 the level of mathematics. And if you divide by 2 10 times, then you have 1,000 times less. This is part of the mathematics. So it's 1,000 times less. It's already, I think, okay. So one of the things which made a lot of noise when it was discovered is the following. Suppose that I'm counting how many links are pointing to a certain node on the www. Now, nowadays, we know that that it's very unequal and that some sites are very famous and some sites nobody looks at them, like mine. In fact, I'm not even keeping my site. I forgot to pay the tax for having a site, so I don't have a site, and I'm not less happy of that because of this. But at the beginning of the story, when www wasn't very well known, in principle, you could think, well, you know, maybe the distribution, maybe the probability to have a certain number of incoming links in a site, maybe it's a normal distribution, which would mean that, let's say, will vary between 20, the average will be 20, and some people will have 1, and some people will have 30, and that's it. And it turned out that it's not at all the case, that there are, and again, in order to make the connection with what I said, it's a power law before. There are, let's say, 1 million of sites which have only one link sending to them. And there are 100,000 with 10 links, and there are 10,000 with 100 links, and there are 1,000 with 1,000 links, and there are 100 with 10,000 links until we get that there is somebody with 1 million links, just one, but very important. That is an example. In reality, there are probably, the numbers are much bigger, but I used that numbers in order to explain again that it's a power law, power in the sense that it's 1 over the number of links is the number of sites, which is proportional. Is proportional. The number of sites is proportional with the number of links is inverse proportional to that number of links. Again, it's not exactly the power 1 of the power 1 of the number of links, but some other power. But to this Ram, is it okay?
Yes, it's okay.
Okay, so you see, it's a very different thing, and it already explains something. Well, it doesn't explain because I didn't explain to you why it is so, but it shows to you that the way of characterizing the distribution of links in the network is not doable if we are sticking to the ideas, to the concepts of the normal distribution. Now, I'm going now to do another step for which I need your help, Ram, because you see, if I try to draw here both the links which are 1 and which are 10 and which are 100 and which are 1 million, then the x-axis will look very problematic, because 1 and 10 on a scale in which 1 million is here will not be will be one on top of the other. I will not be able even to write 1 and 10 because the 10 it will be already much longer than the distance between the point which is 1 and the point which is 10. Ram, is it clear what I'm just said now?
No, what you just said now isn't clear.
Okay, look at the little cross.
I'm looking.
Suppose that 1 million is here, okay?
Okay.
I 1 million is here. Then 10 will be here, very close to 0.
Right.
And if I write, even if I try to write the number 10, I will not be able. So this graph is very difficult to make. A graph which contains both 10 and 1 million is very difficult to draw in this way.
Ah, right. Okay. Okay.
So what people do is the following. They say, look, I'm going to put on the right axis, on the x-axis, I'm going to put at equal distance, not points which are different by the same difference, but which are different, which are differing by the same factor. So I put 1 here and 10 here, but then what I put at a distance equal to that distance from 10 is not 20, but 100.
Okay.
And what I put between the distance in the positive direction between above 100 with the same distance like between 10 and 100 is not 200, but it's 1000. So in this way, I can draw the numbers which I get, but with this price that from now on my axis is not uniform, so to speak, but it compresses the big distances to distances which are smaller. Okay.
Yes.
And in this way, I can draw a graph. This is why on this graph, in which the number of links is like 1, 2, 3, 4, 5 at equal distances, I didn't put the numbers because I couldn't draw anything. But on this one, I can really put the measurements. I can really put how many sides have one incoming link and how many they have 10. And you see that when I throw the numbers before, I was not really very precise. But here you already that 10 links is around 1,000, and 100 links is around 100. You see?
Yes.
I can show in figures, in pictures, what I said in words. So in a sense, it's much better because you saw that it was a little bit awkward to explain what is the power law in words. But now, when I put it on this kind of axis in which the distance between 1 and 10 is like the distance between 10 and 100, and the distance between 100 and 1000, it's like between 10 and 100. I can, first of all, I can show numbers which are very large, which otherwise I couldn't show. But on top of this, you see something very interesting. The power law looks like a straight line on in such a way of putting the numbers.
Right.
This is not by chance. This is this is very useful because you see, when I look at this line here, I cannot say if it is a power law or not. It's a curve which our eye cannot really distinguish what exactly is. But on this line, our eye is very good at detecting straight lines. So when we make graphs, and we see a straight line. When we make graphs on this kind of coordinates, and we say see a straight line, we see, this is a Pareto distribution, as opposed to a Gaussian distribution. As opposed to a Gaussian distribution, let me close my my telephone. Even though the lecture is almost finished, but so when I do this, the Gaussian distribution looks like this. It's limited between very small values. This is the average, and this is the values which larger than this would never happen, and smaller than this will never happen. And we see that in reality, lower than this happens a lot, and larger than this happens a lot. So unfortunately, it's 2 o'clock, and I don't want to abuse your time. I don't do this at conferences either. I don't like to speak more than the time I'm allocated. But I'm very happy that I reached this point. But Ram, please tell me if this graph I succeeded to explain.
Yes, I understood that the fact that I understood that the graph is straight, and like most of the peoples are in the extreme poor,
Yes.
and less on the rich side, and the medium is less than the extreme poorness. The medium average like economy is the medium. How do you say?
Okay. Now, to everybody, the way I give marks to this course is not by an exam. Each of you, unless you really want it, if there is somebody which wants to make an exam, I can give him or her an exam. But for the default, so to speak, הצורה שאנימציה לכולם, אם הם לא רוצים לעשות עבודה בסוף או עבודת סופית או בחינה, מה שאני מציע זה שכל שבוע אתם שולחים כהומוורק, ואני הכנסתי באתר מקום להומוורק כזה, וההומוורק, how did I switch to Hebrew? When did I switch? I didn't switch. I'm tired already, but it's at the end of the lecture. So what I'm saying is the following. One of the ways of getting a grade for this course is that each week you write a small report, let's say about 1 page, about what you understood from that lecture of that week. And the final mark would be the average of the marks which you get for each week. In the previous course of the last year, basically the marks for each report were very high, around 90. And if somebody got a grade which was less than 90, was because not everybody gave reports to every week. But from my experience, one way for me to check that you actually follow the course and without really asking you for any mathematics is that you just write what you understood. It's okay, Ram?
Yes, very good.
It's very good way.
So, thank you for.
I have a question.
Yes.
Can you please loading a recording to the Moodle?
It's put automatically recorded. All the models are recorded automatically.
We will see a recording in the Moodle now.
Yes, yes.
After the lesson?
Not immediately. It takes them hours because these are very big files. But by tomorrow, the recording will be on the page. There is a place called Panopto, a little square there on the main page of the course in which the recordings appear. Or if